Hello, I'm Alex Howe, and this is the Science Meets Fiction Exoplanets review for July of 2022. There weren't really any headline planet discoveries last month. There were a couple that were kind of interesting, but nothing extraordinary. But as is often the case, there was a lot of other work in the field of exoplanets going on that was a lot cooler. Just a heads up on one ongoing project, the Korea Microlensing Telescope Network. This is a survey to find planets via microlensing, and they've been diligently publishing a few papers every month. But honestly, I'm waiting for the eventual review paper to really get a good picture of what they're doing. Still, it's a good project that's worth following. Plus, I like how they call finding large numbers of objects mass production, and also how mass production is about 4 planets per month. Microlensing is a weird branch of the field. Anyway, the first paper I really want to talk about is this one, Unbiasing the Density of TTV-Characterized Sub-Neptunes, Update on the Mass-Radius Relationship of 34 Kepler Planets. Now, TTVs are transit timing variations. These are small distortions in the orbital period of planets, usually on the scale of only a few minutes, that are caused by the gravity of nearby planets. And this is similar to how Neptune was discovered in our own solar system from deviations in the orbit of Uranus. And transit timing variations can be used to estimate the masses of exoplanets. But it's not as good a method as radial velocity, and sometimes gives unrealistic results. In particular, it often gives results of very low densities, suggesting that these planets are superpuffs, which are this class of planets with the density of cotton candy that models continue to struggle to explain. However, this team went back and looked at 34 TTV planets and just reanalyzed their light curves with a better algorithm to get better mass estimates. And when they did that, they found that these very low density measurements increased to something more normal. So here's the before and after. And on the right, you can see the purple line, which shows 2 particular planets and how far their estimates moved. But in general, this whole cluster of low mass estimates, low density estimates, has moved to the right into not quite the same region as radial velocity measurements. It's still a little bit less massive, especially down around 2 Earth masses. But it's a lot closer to normal. And if you look at composition tracks, all of them are well within the 1% hydrogen mass range, which is typical of sub-Neptunes, many of them lower. They could be water worlds, or they could just have thin hydrogen atmospheres. Either way, this study has brought those TTV planets much more in line with existing models. Next up is a new estimate of the occurrence of hot Jupiters. Hot Jupiters, of course, were the first exoplanets to be discovered, but they're actually fairly uncommon because, despite being the first ones we found, it is rather unusual to have a Jupiter-sized planet that close to its star. And in this paper, Belesne and Kunimoto looked at test planets, which provide a larger sample than Kepler, especially for short-period planets, to refine estimates of hot Jupiter occurrence. And they especially refined it for type A stars. These are more massive stars, close to the most massive stars that are known to have planets. And they found that the dependence on stellar mass is weaker than was previously thought. There is still a difference there. Lower mass G-dwarfs, like our Sun, have significantly more hot Jupiters than type A stars, but not as many as we thought previously. And why there is a dependence, we're not entirely sure. It could be due to tidal effects because A stars and G stars have very different tidal properties. And low-mass stars, K and M dwarfs, do have fewer hot Jupiters just because they have fewer giant planets in general. So, interestingly, hot Jupiters seem to peak around Sun-like stars. For something a little more speculative, here's a study on the detectability of exo-moons. Theoretically, exo-moons should be orbiting exoplanets, but we've only found a couple of candidates, and as with many things in the field of exoplanets, they were far outside what we expected. So this paper took a look at how easy or difficult it would be to detect exo-moons using different detection methods. And in this case, red is more detectable. For direct imaging, smaller host planets are better. For transits, larger host planets are better. Radial velocities, larger and short period. Astrometry, that's tracking the motion of the star in the sky, which is what Gaia does, larger and long period. And in the bottom left, that's transits again, but that is looking at transit time rather than the size ratio between the planet and the moon. So a long transit time, of course, is better, but those will also have fewer transits, so they're harder to spot for that reason. So this suggests that there are significant regions of the parameter space where we could detect exomoons, but it's still pretty difficult. Moving on, looking at the architectures of planetary systems, I think this may be the biggest paper for the month of July, Edge of the Multis, Evidence for a Transition in the Outer Architectures of Compact Multiplanet Systems. And this is looking at what are sometimes called the compact Kepler systems, where you have many super-Earth or sub-Neptune-sized planets orbiting very close to the star. And the question is, are we seeing all of the planets that are there, or do there continue to be more of these closely packed planets moving out, because as you move farther from the star, any small tilt in the orbits of the planets will bring them out of the plane of the star so we can't see any transits. And this team looked at known multiplanet systems and calculated if there was another planet there, how likely would we be to detect it? And they found that we should be able to see more distant planets. And the fact that we don't see any additional planets in these compact systems does not seem to be down to chance. We wouldn't see all of them, but we would see some if there were more planets there. And this is very interesting, because when I went to the Exoplanets 4 conference in May, one of the plenary talks was by Konstantin Batygin, who is one of the rock star scientists in this field. Literally, he plays rock music. And he gave a talk talking about formation models of these compact systems. And the latest formation models line up with this study showing that the compact systems are limited to the planets we see. And I'm still waiting on the paper to go with that talk, but the short version is current models suggest that 4 or so planets will form out around the 1 AU range, and if these planets grow large enough, interactions with the disk will cause them to migrate in toward the star and become a compact system. But less massive planets, without a whole lot of in-between, will stay put. And that gives you a system that looks a lot like our own solar system, with 4 planets Earth-sized or smaller out around 1 AU. And since the compact systems don't show the hypothetical additional planets, that is some good evidence for this formation model. So that's really exciting to me. Here's a fun little paper about which exoplanets will have diamonds in them. Now, it's been speculated for a while that carbon-rich planets could have interiors that are made of diamond. Maybe even a mantle that is mostly diamond as opposed to olivine like on Earth. And this could happen toward the galactic center, where there are older stellar populations that produce more carbon than oxygen. But these authors suggest that diamonds could also form in low-carbon conditions, such as we have in our solar neighborhood and our solar system, due to phase transitions, which could cause carbon and oxygen compounds to separate from each other in planetary interiors. And in this plot, the blue shaded region is where that's most likely to happen. And of course, there's some fuzziness in it, and other people have predicted different regions, but in this case, the blue shaded region of temperature pressure space is where they expect to find diamonds, and Neptune could have diamonds in it. Uranus probably not, because it's a little warmer. And that is interesting because formation of diamonds releases heat. If you've taken a chemistry class, you'll recognize that as heat of crystallization. And that could explain why Neptune is much brighter in the infrared than Uranus, because it has more internal heating from this crystallization. So, a lot of work needs to be done to try and confirm that, but it's an interesting hypothesis. Next, another big story of the previous month was a trio of papers about the formation of rocky planets. And this was a very big project to figure out exactly what's going on in pebble accretion models. Pebble accretion is a formation model in which planetary embryos form, Mars size at most, probably smaller, I think, and then they sweep up pebbles, which are not pebbles in the geologic sense, but in the cosmological sense, around the 1 meter size, and they sweep up all of the solids in the protoplanetary disk in this pebble form to coalesce into larger planetesimals. And the actual process is probably a mixture of pebble accretion and planetesimal collisions, which are the more traditional formation model. But the main thing is these papers studied the physics of pebble accretion on many fronts, but especially with regard to aluminum-26. Aluminum-26 is a radioactive element produced by supernovae, which can be sort of seeded across star-forming regions, because supernovae tend to happen in star-forming regions, and then become incorporated into the next generation of stars and planets. And heat from the radioactive decay of aluminum-26, and also iron-60 probably, is believed to play a major role in the formation of planets. So just to give an overview of what they did, they had a geochemistry model, and this is kind of confusing with the abbreviations they're using, but they're looking at a mixture of metal, silicate, and water, which is what a lot of more distant asteroids and comets are made of, just all the elements mixed together. And that can be separated into water and solids. It can be metal and silicate, metal oxide, just silicates, just metals, and so on. And they ran this model through 2 pathways of planetesimal formation. One is based on the asteroid Ceres, which does not appear to be strongly differentiated, still appears to be very primordial. And this plot shows the internal composition of the object. Left to right is outward from the center, and bottom to top is forward in time. And the green is this undifferentiated metal silicate water mixture. And as the heat from radioactive decay built up, the water melted and moved toward the surface. Ceres' surface is very ice-rich compared with, say, the moon, even though it's not up to the level of outer solar system moons. And that's about it. The interior is believed to be still more or less undifferentiated. Whereas Vesta is more water-poor, and also appears to have undergone 1 or more giant impacts, which would have added additional heat to the system. Vesta appears to have lost its water, probably to a mixture of giant impacts and evaporation, forming this dry orange material, and then the heat caused it to melt all the way through, which is what allowed, even for such a small object, an iron core to separate out from a silicate mantle. And they did a similar study with an Earth analog. In this case, it's a cross-section of the Earth, but time is now clockwise around the circle. And time is in millions of years, so it's simulated for 5 million years. And on the left is composition again, and on the right is how much of it is melted. And if you look at composition, the water separates out and comes to the surface, and at some point, the heat builds up enough that fairly quickly the planet melts all the way through, and the water evaporates and most of it is lost. And you're left with an iron core and a silicate mantle. And they also looked at how this affects atmosphere formation. The initial hydrogen and helium atmosphere from the protoplanetary disk will evaporate away, and a new atmosphere will be outgassed from the mantle. And this is with a lot of carbon-oxygen compounds and some nitrogen, which would be about what Earth's atmosphere was thought to be before life arose. And there was a lot of stuff in these 3 papers. I didn't even have time to get to all of it. If you're interested in them, you can take a look for yourself. Speaking of atmosphere formation, there was another paper that touched on this subject. Impact-induced atmosphere mantle exchange sets the volatile element ratios on primitive Earths. And this is looking at the amount of volatiles in the atmosphere of an Earth-like planet. These plots show the amount of volatiles in the atmosphere and the mantle of an Earth-like planet as it grows. And note that volatiles includes water, and a significant amount of Earth's water was believed to be in the gas phase initially while the planet was cooling. So that's why the numbers are much higher than 1 atmosphere. And in fact, Earth's oceans contain 200 or 300 atmospheres of water. So that kind of number would be what we expect for the atmosphere. Now you'll see the purple line going up to 1,400 atmospheres of volatiles in the atmosphere. but that line is for no impact losses. Giant impacts will blow the atmosphere away from the planet. On the other hand, on the right, you'll see the brown line, which is the amount of volatiles in the mantle, reaches 5 or 10 times the amount of water in Earth's oceans. That may be the case, but we don't think it is. We think the mantle has some water, but maybe only one ocean's worth. And the brown line is a model where there's no exchange of volatiles between the mantle and the atmosphere. So, as I said before, outgassing from the mantle can create an atmosphere. And when it's included in the model, the mantle retains much less volatile material. The yellow line is if there are no giant impacts, and giant means like planet-planet collisions. And the blue line is the reference model, so that's close to what we think actually happened. And this shows that both outgassing from the mantle and impact losses are critically important to getting Earth as we see it today. Now, this is probably the next biggest paper from last month, detection of atmospheric escape from 4 young mini-Neptunes. And in fact, Anton Petrov did a video on this paper recently, and he suggested that it was strong evidence for photoevaporation. And that surprised me a little bit, because I have studied photoevaporation in particular, and the information I've seen over the past year or two has been swinging away from that and toward something called core-powered mass loss, which is basically the heat of formation of the planet causes the atmosphere to puff up and blow away, as opposed to being ionized by ultraviolet light from the star. And part of this revolution has been from improved models, but another key piece of the puzzle is that in the past few years we've been taking a look at the helium line at 1083 nanometers, because this spectral line is a very good diagnostic for the escape of a hydrogen-helium atmosphere from an exoplanet. And crucially, we don't just measure the rate of loss, but we measure the velocity of the outflowing gas. And that's the key point from this paper. The researchers here looked at 4 young mini-Neptunes, younger than 1 billion years old, so we would expect them to still have some mass loss going on. And they found a hydrogen-helium outflow moving about 3 times faster than you would expect to see from core-powered mass loss, which is much more consistent with photoevaporation. So this suggests that photoevaporation is a major contributor to mass loss after all. But it's not the full story, because there was another paper last month, the K23 system revisited, testing photoevaporation and core-powered mass loss with 3 small planets spanning the radius valley. So here's the mass radius diagram for the K23 system, and you can see there are 2 planets down around not quite down to the solid rock line, they could have some water, and then a 3rd planet that is large enough in radius that it probably has a hydrogen envelope. And if you plot it on the radius installation diagram, which is close to radius versus orbital distance, and map where the evaporation valley is, K23b is above that line in the mini-Neptune range, and the other 2 planets are below that line in the super-Earth range. And planets that are in the same system like this are great laboratories for evaporation mechanisms because they were subject to the same irradiation from the star except for orbital distance. And what they found is that planet B, which is a mini-Neptune, should have lost its atmosphere, but doesn't appear to have lost it, because it's closest to the star. If it has enough gravity, it could retain an atmosphere, but it's not that large. And the thing is, this is not consistent with photoevaporation or core-powered mass loss, which, if you look at the graph, have very similar signatures. My hypothesis for a while has been that it's going to be looking at different stellar types that will disentangle those. And since it's not consistent with either of those, it's not clear what's going on. It could be something with formation, it could be migration, maybe impacts on K23c, although that doesn't really explain why planet B still has its atmosphere. So there are still some oddities regarding atmosphere loss that are not fully explained by the photoevaporation model. And I can't pass by atmospheres without talking about JWST. This was the paper connected with that first planetary spectrum that was released from JWST on July 12th. And there's not a lot that's remarkable about this. It's a spectrum of a hot Jupiter, And they specifically picked one that they didn't think would have a whole lot of surprises because they wanted to make sure the instruments worked as well as they expected. So it's a spectrum of a hot Jupiter, has some very clear water features. We believe there's water vapor in most of these planets' atmospheres. And it doesn't tell us a whole lot directly, but it is a very good spectrum. And that promises much more interesting discoveries to come, and in fact, just a few days ago there was one about carbon dioxide found in the atmosphere of an exoplanet, and that'll definitely be in next month's review. Talking about habitable planets, or potentially habitable planets, there were a couple of papers. There's Salty Ice and the Dilemma of Ocean Exoplanet Habitability, and this is the issue that if a planet is a water world and has many times as much water as Earth does, then its oceans could form high-pressure ices at their bottoms. Because when water's under high pressure, it's compressed into ice that is more dense than water and doesn't float on the surface. Now the problem is, if the entire ocean bottom is a layer of ice, which it probably would be if it's more than 100 kilometers deep, then nutrient-rich material from the mantle might not be able to get through it and seed the ocean. You need the carbon and sulfur and phosphorus compounds from the mantle to form life. And the problem is even worse because, unlike normal ice, high-pressure ices can be salty. And salty ice will be even denser and will further limit convection from the mantle. So what Baptiste Journeau did was look at the expected structure of an ocean world as compared with an icy moon from our solar system, and calculated how the convection would work, and found that, in fact, there could be convection from the mantle up through this high-pressure ice layer. Because if you've studied geology, you know that Earth's mantle is not actually liquid for the most part. It's mostly solid, but there's still convection because on scales of a planet and millions of years, even solid rock behaves like a fluid. And the same will be true of solid ice. So there can be convection even in this ice layer, which could allow nutrients from the mantle to reach the liquid ocean. So that's good for ocean worlds. We also had this paper, Stellar Metallicity is a Key Parameter for the Search for Life in the Universe. And this was kind of an odd one to me. So the basis here is that even though the building blocks of life as we know it are these light elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, transition metals like iron play a large role in biochemistry on Earth. And it's not just iron. Cobalt is found in vitamin B12, manganese is in something, vanadium's in something else. I'm not a biochemist, but a lot of these transition metals are actually micronutrients and are very useful in catalysts. The thing is, transition metals are not evenly distributed in the universe because they're produced mainly by type 1a supernovae. So much like the aluminum-26 I mentioned earlier, they would need to be seeded in a star-forming region by a nearby supernova. And they suggest that life may be unlikely to occur where these transition metal abundances are out of whack. The thing is, if you look at the actual origins of these elements, the basic building blocks of life, especially oxygen, also come from supernovae. So a planet is very unlikely to be lacking transition metals while still having the basic elements of life. And also, thinking of speculative biology, I think life could evolve a way around them. I don't think they're really that essential. So it's an interesting thought experiment, but probably not as relevant in practice. And finally, we have a fun little paper about parallel universes, which is not really a whole lot that's new, but is still fun to think about. And this is planetary systems with forces other than gravitational forces. So in a parallel universe, gravity might not necessarily follow an inverse square law like it does in our universe. And in our universe, the inverse square law produces orbits of planets which are nice, neat ellipses. And Soren Toxverd, sorry if I'm pronouncing that wrong, calculated what kind of orbits planets would have if there were some other central force, F proportional to r to the x. For an inverse linear force, you could have overlapping cloverleaf-shaped orbits. These orbits are stable. They'll stay put over cosmic timescales if gravity is an inverse linear force, but they overlap in ways that almost certainly could not happen in our universe. And they can get weirder than that. Inverse cube forces, however, don't work so well. All orbits with inverse cube forces eventually spiral into the star or spiral away from it. And this is something that's been known for a very long time. In fact, Isaac Newton proved it. But these are some fun visualizations that show a side to it that I hadn't seen before, so I thought it was worth sharing with you here.